Okay, good evening everyone. I think we'll try and make a start. It's not as echo for you as it for me. It's very echoey. I'm glad to see so many people made the journey out. It's such a cold night, but it's a very warm welcome, I can assure you. As usual, we've got a pretty busy programme. We've had a little bit of technology trouble, which we're going to have again, don't believe it. Yeah, come on. Right, okay. Okay, has everybody got their news sheet?
Yep.
Right. Good job, John. Terry has got the book, the attendance register there, if you can fill it in before you go. We're just going to do some coming up in the sky, and then Terry's teacher as usual. And the main speaker tonight, we're delighted to have a good friend of the association, Professor Jerry Doyle. And we're going to have some tales of solar astronomy. It's not a very solar astronomy night, sure it's not. It's pretty cold tonight. Anyway, let's start off with a look at the sun. Very usual. But we'll try to turn that off. As you know, they come back up again themselves, totally unprompted. So forgive me for that. But this is a picture actually of the sun yesterday. And it's just to see how active the sun actually is. Look how many different spot groups are on the sun. And this particular one here, 3165, has really been kicking off over the last couple of days and produced some really fantastic aurora up around Iceland and the polar regions. So keep looking out. You never know, some night might be our lucky night. And this coronal hole as well has been pouring stuff off into space. And I'm pretty sure you're going to hear something else about coronal holes before the night's up. Now, most of us will be familiar with the 11-year solar cycle. In fact, some people talk about a 22-year solar cycle, but actually some people recently at Stanford University have done some research about the magnetic field on the surface of the sun. And it is revealed that in fact there isn't an 11-year cycle. In fact, there are two parallel cycles running simultaneously. Can you see that okay, or do you want the lights down? I'm happy to keep pressing that button. Okay. So what they've found is in fact that there's two overlapping cycles, and those cycles are actually 17 years, each. And just like as if, some of those songs where you start and then a few beats later someone else starts, well that's the way these patterns run. And just because of the way they run, it actually, you end up with an 11-year cycle. I'm sure it's much more complicated than that, but that's my explanation. And it's actually showing that there's interesting stuff going on deep inside the sun. So I'm sure again we might hear something else about that before too long. Now of course it's all about the planets at the moment. And did anybody see the occultation? Keep your hand out, Terry. Did anybody see it? Well, it started off lovely. I was round at my daughter's house and I happened to look up and she says, "What's that close to the moon?" I said, "It's Mars." And later on tonight, Mars is going to, pass behind the moon. And I was very excited, rushed home, got my cameras all set up, got everything ready, and of course, our good old friends the clouds came. But this was a photo that as soon as I got home, I thought, this is brilliant, this is really going to be good for us. This is a wee bit later on. This is a photograph by Paul. And it's a brilliant photograph because you can also see got Neptune down in here. It's very unusual. Very unusual with a handheld camera phone. But anyway, it's not Neptune, by the way, it's some sort of artifact. And then Simon, he got a picture of a pulsar, which is very unusual as well. With the jets coming out, pretty impressive stuff, Simon. And actually he managed to get this picture with Mars pretty close in. So that was pretty impressive, I have to say, Simon, well done. Did you actually get to see the occultation itself?
No, don't go back in the house.
I got up at 4 o'clock in the morning and went outside and it was raining, so sorry about that. Obviously, if you get Mars good, I was just talking to John, who's been taking some fantastic images of Mars, you can see some good detail. Now, I've got a pretty good telescope, and to be honest with you, Mars usually looks pretty bland, but this was an image I took last week, and you can actually see something in terms of detail. If you look over here, there's a very famous feature called Solis Lacus, and that's the eye of Mars, and you can sort of see it over here in my new picture. And then if you look again up and around here somewhere, you can see one of the small ones. you can just see it as a white patch. So you can see some detail, and I can't wait to see John's pictures from last night because he said they were fairly good. So, yep, get out and have a look at Mars. You can actually see a wee bit of the polar ice cap as well, over there, right? Which visually, I have to say, can't see very much of. Also, Jupiter's still there, and Jupiter's pretty impressive. If you get a chance, you probably saw it on the way in there, shining brilliantly. I was away last week, the week before actually, in Monaco with work, and the sky was clear every single night. So I had them playing this week game. Is it Mars or Jupiter? You know, and every night you come out and go, is that Mars on there? No, it's Jupiter. But you know, that's what you do in Monaco. Anyway, okay. Just in case you're not too sure where the planets are, still a chance to see Saturn. Saturn's moved down over here in the west. Turn the lights out there. Just to get the look. Saturn down in here, and Jupiter up here, and quite close to the moon. Around about the 28th, 29th. I think the moon's there on the 28th, and it moves up to there on the 29th. So if you haven't had a chance to take a good picture of the moon, Jupiter, and Saturn, still an opportunity. And try and get a look at Saturn before you go. Time's running out. It is dropping down into the west, but it's still pretty good. And the 26th of December, day after Christmas, in case you're not too sure when that is, it's going to be 4 degrees north of the moon. Okay, all the fuss has been about the Geminids, and Terry was on the radio this morning, and did anybody hear him?
Didn't know it goes on,
Good, it was really good.
Okay.
And the Geminids has actually been brilliant so far. I was out last night for a good wee while, and I saw about 6. A couple were quite good, but I captured a couple of dozen on the meter camera. So they're called the Geminids because the radiant is quite close to Castor, which is one of the twin stars in Castor and Pollux in Gemini. The Geminids are actually probably our best star now. We used to say that the Perseids in August were the best star. It looks like the Geminids have got that crown at the moment. The Geminids are a particularly curious star because they are not from the normal cometary dust. They're actually from an asteroid called Phaeton. Now, astronomers can't work out whether it's a rocky comet or a cometary rock, whatever. But you know, it's quite an interesting thing. It's a sun-grazing asteroid, and it is also one that's listed as being threatening because it gets so close to the Earth on occasion. But anyway, the Geminids, you'll probably still get some tonight if it's clear. If you can stick the cold, you know, you'll see half a dozen really. Although the peak is a fairly well-defined sharp peak. There's another wee shower, which is one of the lower category showers. It's called the Ursins. But the good thing is the radiance are way up at Ursa Major, Ursa Minor. You can see it here. 10 metres an hour under perfect conditions. You're lucky if you see 1 or 2. And it is associated with a comet. It's associated with Mackall's comet. And Don Mackall's was a great comet spotter. I can't remember how many comets he spotted, Terry. Quite a few, I can imagine. I think he's still around. But the good news is, still about the planets. At the end of the month, around about the 29th, you'll be able to see way down low, you'll be able to see Venus. And just up about here, you should be able to see Mercury. Now, it's always worth stressing, if you're going out looking for Mercury, wait until the sun drops below the horizon. Probably you might need binoculars because the sky's going to be pretty bright. You can see on the wee clock here, it's only 4:30. 4:30 is still pretty bright, so it's going to be quite tricky. You might need binoculars, but for goodness sake, don't look until the sun has dropped down. But you can see there's a beautiful sweep of the planets. Mars is up there somewhere, Jupiter, Saturn, Mercury and Venus. So pretty impressive array of planets at the moment. And just to finish, did anybody notice there was a new splash at the weekend, a splashdown, on exactly the day that Apollo 17 landed on the moon, 50 years ago. Now, Paul, who most of you know, Paul Evans, he's down in Armagh tonight talking about Apollo 17. And we've got Jerry from Armagh who's up talking to us tonight about the sun. But, you know, it's really exciting now we've got another moon landing program initiated. And it's the first landing on water since the Apollo program, first splashdown. And Sean the Sheep, apparently, by all reports, is fine. So, complete success. Okay, enough of that nonsense. And That's good.
Okay, thanks, Andy. This is not my laptop, so maybe a few hiccups as we go along here. Thank you, everybody, and welcome. There's been slight changes in the title. I met Terry at a conference here in Belfast a few months ago, and of course, when Terry, he twisted my arm and got me to give a talk. So I thought to myself, I won solar physics, I won stellar physics, and I thought to myself, no, okay, I'll change it around, and I'll talk through the various instruments I've used, telescopes, space and ground-based. But by way of introduction, this is a movie here. It comes from the Solar Dynamics Observatory. It's a composite movie based on the first image was a white light image, and these are a series of frames taken every 12 seconds and a series of chrome lines. I can give Terry the website for this. There's a series of these beautiful movies and stills. It's absolutely fantastic. Well, let's see if I can manage this. Okay, right. I'm going to rewind the tape way back till 74 when I went to Queen's. I didn't do physics, so I've never been this lecture theatre ever in my life. I done applied mathematics. I worked with my supervisor was a man called Arthur Kingston. He was also from IAA. And during my first year of in doing computers, or sorry, doing mathematics, we had to use computers. We used an old MBM mainframe. Some of the gold notice here, I recognise some of the computer sheets here, some of the punch cards you had to do years ago. That's how I learned how to do computing. Absolutely appalling way of doing computing. During my second and third year, Arthur basically took a sabbatical during my first year as a student. So he spent some time in two places. One was Harvard Observatory in Cambridge, Massachusetts, and another place was in Naval Research Laboratory in Washington, D.C. And the reason for that is that these two places had. Oh, sorry. I changed the slides earlier on. I forgot what order it is. Right. What I'm going to talk about, I'm going to talk about most of elements, most of the electromagnetic spectrum, except gamma rays. I'm going to talk about X-rays, ultraviolet, infrared, microwaves, radio, and so forth. Go through what different telescopes I've used. So let me go back to where I wanted to go. Right, this is Skylab. I done most of my thesis work based on data from Skylab. Skylab had two excellent instruments. One of those was built by the Harvard, this one in the lab in Cambridge, and the other was in Washington in Naval Research Lab. This image was photographed by the astronauts as they left Skylab for the last time. During my thesis, I used data taken from 1973. The instrumentation that was on the instrumentation report on Skylab were quite old hat compared to the one computers were basically photographed film. In order to reduce those, you had to use a microdensitometer. When after my second year at Queen's, I spent my 2.5 months in IAA, which is using photographic plates from the IAA Harvard Distinct Telescope. And this is basically very similar. The images in the middle, these were images taken by the astronauts on board Skylab, and shows a series of beautiful flare loops. These are the temperature loops are in around anywhere from 2 million to maybe 10 million degrees. The middle spectrum, when you look at the middle diagram, this data taken with the instrument Harvard, it shows a series of beautiful spectral lines. And one of the reasons why Arthur Kingston was very interested in this is that Queen's was probably the best place in the world for doing atomic calculations at that stage. And what he wanted to do was apply their atomic physics data to interpretation of solar data. The times when the observations were taken, the diagram on the right-hand side, there's a series of points. So the astronauts seen a flare going off and managed to take photographic images as we went along. The image on the right-hand side is the Skylab. NASA built two of these. One, of course, was flown, and years later, I think it disintegrated over Australia, I believe. This is the second one. It was there a few years ago in the Smithsonian Observatory. If you ever go there, go and visit it. I was there and I spent maybe an hour and a half. You keep pushing you along, keep walking, don't stop, don't look. I went around 3 times trying to wonder where the astronauts stood, how they made the observations. Absolutely fantastic. I also used data again. This was a rocket flight called Hertz. This was again designed by another group for the Naval Research Lab. The rocket flight lasted less than 5 minutes. This is a series of spectra taken of a quiet sun, 2 sunspots in an active region. And again, I used atomic data from Queen's to interpret these, derive the electron density, the plasma you're looking at. I also spent some time in 1980. SMM, Solar Maximum Mission, was launched. And I spent maybe 4 or 5 months over in Washington, based in Goddard Space Flight Center. Now, I have to say one thing about the Americans is that they always try to encourage young people to get involved at a very early stage. So, despite the fact that I had just got my PhD, they made me planner, the instrument planner for a week. Nearly 2 hours before I took over, some ground computer whiz kid set up incorrect commands and SNM was launched, or lost till Earth. It was found around 4 or 5 months later by a telescope in Puerto Rico, or Arecibo, and I'll come back to Arecibo because I've used Arecibo several times as before. One of the interesting things about repair of SMM was that this is basically, it done NASA really good because it basically showed the American public that you could take the shuttle and repair spacecraft in orbit. This probably looks a boring sort of diagram. There are a couple of instruments on SNM. One was a hard X-ray instrument that had a cadence of about 0.1, 0.2 seconds. Another was the ultraviolet spectrograph, which looked at a series of spectral lines with again very, very high cadence. Unfortunately, this experiment has never been repeated. And what we found out at that stage, this is, 1980, 81, was that the ultraviolet lines lagged the hard X-rays by about 0.2 to about 0.4 seconds. There were various papers. I wasn't involved in any of those, because I didn't really agree with the interpretation. It took me approximately 32 years to solve this problem. And I solved it when I started working with people from the Jet Laboratory in Oxfordshire. They deal with tokamaks. They need very, very high cadence atomic physics data. The data we used way back then were basically time-independent data, and you need time-dependent data. And when you put in the time-dependent stuff, you just basically solve this problem. But it took me 33 years to solve it. Okay, I was involved with another mission, Trace. Trace was launched from the bottom of an airplane. And it's interesting that the UK Space Agency will shortly, sometime next March, April, start launching space vehicles in the same manner, using a Virgin aircraft. This works. Okay, on Soho was a mission. It's probably the mission I've spent most of my time on. One of the instruments on board there was a chronograph, which detects coronal mass ejections. Just like Terry, Mars bars. I've got a few Mars bars. I've got a few questions to go along here. Right. Typical CME. If you're able to put all that mass into big trucks, how many trucks would you need? I'll tell you those today. And you have to be very close to it, otherwise I'll take this Mars bars for myself. Another mission I was involved in was one called Yoko. It's a Japanese mission. I had to spend about 3 or 4 weeks out in Yokohama. And I remember after about 2 or 3 weeks I had to go to the bank to get some local currency. And I had to pass by, it's about maybe a 15, 20-minute walk, and there was a train station. And as I passed by, there was a heavy goods train passing by, and the driver was shaking. I thought, God, what's that train carrying? About 15 minutes later, I was in the bank, and the news flash came on, earthquake in Yokohama. So I'd witnessed an earthquake, and I didn't know it. Now, one of the things that instruments like was thrown on Yoko showed was that flares, you look at flare loops now, if you look at, there's a little white slit here over a loop plate again, and on the top panel you'll see these oscillations. And that's now been observed in not only solar flares, practically all flares, but also in stellar flares. And again, I'll show you some more of those. Another mission that was launched from the Admiral plane called IRAS. IRAS is still functioning. The ground station is in Lockheed in California. This is an image of sort of prominence eruption at the limb. It's a beautiful, beautiful movie sequence. IRAS basically has been observed for the last, I don't know, maybe 10, 12 years. Fantastic data. For the first maybe 20 years of my research, I basically was entirely done with data from space. But I started several years ago to get involved in ground-based solar physics. And the first place I went to was a place called the Dome Solar Telescope. It's in New Mexico. Now, some of you might think New Mexico is all desert, but if you go into northern New Mexico, there's a lot of mountain range there. The Dome Solar Telescope, it's above ground. It's like 100 odd feet above ground. Most of it's actually below ground. It's more than 200 feet below ground. The really interesting thing about it is that the whole assembly, 300 odd feet, actually floats on Mercury, bed of Mercury, for stabilization purposes. And one of the reasons why we used this instrument was that if you look at different spectral lines, I have here lines due to iron 1 and calcium 2. I'll play this movie again. The iron 1 line is formed deep in the photosphere, calcium 2 is formed higher up. And as you go from, for example, if you take the calcium 2 line, I'll play the movie again. If you look in the wings of the line, what you're looking at is basically the photosphere, the cooler region. As you go to the line core, you'll see the chromosphere coming in. Unfortunately, I can't stop it because that's not my laptop. There's my photosphere, there's the chromosphere. I know there's groups here in Belfast been using this instrument as well. You've been using it. It's an absolute class instrument. In more recent times, I've been taking trips to La Palma and using the Swedish Solar Telescope. The image on the left, some of you probably recognize some of those telescopes. WHT is the one on the left-hand side. The next one up is the dot, is a small solar telescope, it's no longer used. The one in the middle is the Swedish Solar Telescope. And the two telescopes on the right-hand side, one is the INT, second last one, and the other one is a 1 class meter telescope which hasn't been used probably 20 odd years. I think there was some Irish involvement and one's from Galway involvement years ago, I seem to recall. I can't remember what it was called. This again is some of the data. I think some of the data that the Swedish Solar Telescope produces is probably better than what you get from the Dun. It's sharper images. Again, this is calcium 2, and when you scan from the flying wings, you see the photosphere through the chromosphere and back. And we've used that to observe a series of solar features, spicules, sunspots, numerous regions. This is another place, this is in California, called the Big Bear Observatory. If you ever find yourself out in that part of the world, go and visit there. It's actually midway between Los Angeles and Death Valley. Gorgeous place. And if you happen to go there in winter time, you can go skiing there as well. I never went there in winter time. Lovely place. Now, one of the telescopes with ourselves, NAMA and Queen's and other UK groups have been involved in is a new telescope called DKIS. It's a 4-meter class telescope. It's based in Maui. It is operational, although not fully operational yet. I haven't managed to get data, although I've got successful posting now with data. Now, I have not question. The image on the right is probably the highest resolution image ever taken of the Sun. So for not Mars bar, can somebody tell me the size of one of these cells compared to Northern Ireland? Approximately.
There's a clue.
Sorry?
In Texas there. Still in Texas, there's a lot of that fire.
Oh, that's the older version, sorry. Yeah, yes, okay, Texas, well, okay. I'm living in Texas. Unfortunately, right, when you asked me to convert to PowerPoint, I didn't take the more recent version, which had Northern Ireland. Bloody hell. Right, now, I mentioned over dinner, I've used the Lick telescope in California. The Lick telescope, or Lick observatory, is a stellar instrument. I decided to do something entirely different and use it to observe the Sun. And the reason for doing that is that, unfortunately, in solar physics, we do not have on a shell spectrograph like they have for stellar astronomy. So what we use in the Lick, in order to cut down, the Lick is a very, very large telescope, so you have to make a few adjustments. You have to put a big bit of cardboard over the telescope to cut down the light, and then you include a few different filters as well, again to cut down the light. But the good thing about this is that it allowed us to get basically a full spectrum over the total from about in around 3,500 hours up to about 7,500 hours of the solar spectrum during a flare. And what we have here is observations in a few of the Higgs-Barmer lines of a flare and a non-flare region. And we're able to get very interesting physics out of this. Some of you have been down the board. The telescope on the left-hand side is not your conventional type of telescope. They're basically a series of radio antennas sitting on the ground. They don't move. Steering of this type of telescope is done with software. Earlier this year, we managed to observe a fantastic solar flare with a coronal mass ejection. We're currently working on that data, which hopefully will be published sometime early next year. If you look closely at the light curve, you can see there are a series of short period oscillations again. And again, that gives us information on the magnetic field strength we're looking at and the loop lengths. From when I told Terry Hegel originally, I said solar physics, but I want also do a bit of work in stellar astronomy as well. So I've done a lot of work in using the notified Explorer mission. And this basically allowed us to observe all the stars the same way and observe the sun for many, many years. The ground station for this mission was outside Madrid. Again, a very nice place to visit. I was there maybe several times. I've also used another ultraviolet instrument, one called Galax, which basically it had very high cadence instrumentation, basically with sub-second cadence. These are a series of flares that observed. When you look at it in more detail, you can see these short-term oscillations of order of 30, 40 seconds. Again, that allows us, provided you can narrow down the emission mechanism, it allows you to estimate the field strengths for the flare on the star. I've also used another Japanese mission called Ginga, and this probably involved. This took a lot of my time. I not only used Ginga, but I also used the IAA for the ultraviolet, but I used the 78 ground-based telescopes. And this took a lot of organisation, and remember that this was in the very early stages of emails. So you had to have a lot of telephone calls, a lot of letters, but we managed to get fantastic data from a range of different wavelengths. I've used a series of instruments. I've used another X-ray instrument, it's in the ESA mission. I used an extreme ultraviolet spectrograph that basically meant I had to go to California in Berkeley. I used an infrared spectrograph, and that was the headquarters that was based in Oxford. As I said, I've been to La Palma many times. I've used a lot of telescopes there. I've used the INT, WHT, SST, and a large Spanish 10-meter class telescope. Years ago, whenever you travel from here to La Palma, it basically took almost 2 days to get there. You had to fly Belfast, London, Madrid, Tenerife south, overnight there. Taxi next morning up to Tenerife north, and so forth. Now you can get the telescope in the same day. It's absolutely amazing. Now this probably looks a bit boring. This is data taken on the INT. It again shows their calcium HK line and shows some of the Heisenberg lines. Now there are two weak lines there. One is due to helium-1 and another is due to manganese-1. The calcium-2 line, given term diagrams, I'll try to explain this as best I can. So while I'm using wavelengths, I'm going to use frequency. Many of you're driving in your car at night time and you listen to a radio, and you drive in a big city, and all of a sudden you get interference from another radio station. And it's almost the same here. Magnesium-2 is formed in the chromosphere, so when a large flare goes off, the line not only increases in intensity, but increases in line width. There's another line formed at a very similar frequency, slightly distant, not that far. So what happens is that your magnesium-2 line increases intensity and width, and photons get transferred into the manganese-1 line. So manganese-1 is formed in the photosphere. It should never ever go into emission. And what makes this really interesting is that one of these manganese-1 lines has been used by people in Kip Peak for years and years to monitor the temperature of the sun. When this was published 15, 20 years ago, it basically meant that approximately 40 years of data that it obtained was almost meaningless, for this particular line, because they assumed this was coming from the photosphere. And when they looked at the line, they couldn't understand why there were, they looked at light curves, why there were times in which the intensity of this manganese-1 increased, And it's because you won't look at a foot sphere, you're looking at a chromosphere. I've been to South Africa many times. I was there a couple of years ago, about 3 years ago. There are approximately 16 telescopes in SAO now. When I went there years ago, there were only 4. I used 3 of those telescopes in my visits there. And of course, one of those is SALT, in which AMA are involved in as well. I mentioned using a Steppler telescope to observe the sun. Well, when I went to Kitt Peak 21 years ago, I used a solar telescope to observe the star. I have to say the observations were not all that successful, partly because we had instrument problems and also weather problems as well. So it wasn't the most successful trip, but it can be done. More recent times, you've probably heard of Kepler. Kepler was a mission launched to find and detect exoplanets. It also was a very, very fantastic mission to look for stats on the occurrence of flares on a particular star. Now, if you're using a ground-based telescope, you only observe an object for a few hours a night. Whereas with Kepler, it basically observed the same part of the sky for about three and a half years. So you can build up fantastic stats on flare occurrence. I'm also using another mission. It's still functional. It's called TESS. And we're doing basically similar things. Now, one of the things we find with TESS is that when we go to very fast rotators, stars that rotate on a period of 0.2, 0.3 days. The theory basically tells you that the faster the object is rotating, it should enhance flare activity. What we see here is the opposite, and we're still trying to figure this one out. And we've got a series of proposals over the last series of telescopes the last few years, and we still haven't figured this one out. I've also been to Hawaii several times. I've used different telescopes in Hawaii, millimeter telescope, the infrared telescope. I've used numerous, I've used a small telescope. The bottom right hand corner was taken with a small optical telescope, which actually no longer exists. It's been replaced by one of these 10-meter class telescopes. I get which one. One of the things that I done way back about 1980, when I got telescope time on the JCMT. What you see here on the right hand side, you see a series of points and then you'll see a curve out of there. That is basically the Planck function or black body curve. And it fits most of the points very well, except when you get up to the far infrared and particularly get the millimeter wavelength. And there are basically only 2 interpretations for this. One is that you either have a cool object orbiting the star, or you get mass loss, similar to a solar wind. And unfortunately, our paper, which was published in 1981, we picked the wrong mechanism. We assumed it was, we modelled it and done calculations for mass loss. 3 years later, in 85, 86, I was at a conference in Italy and a guy reported the first detection of an exoplanet. We hadn't discovered this 6 years earlier, except we got it all wrong. If only. The most recent telescope I've been using is one in Thailand. It's a 2.4 meter class telescope. And I'm using this telescope, I've used it now twice. I used it to look for oscillations on flares, and again we find a series of oscillations on flares. But what I'm currently, in fact, as we basically speak, I've been awarded 5 nights telescope time in December or January this year. One night is ready, going up. I have now 2 nights on the 23rd and 24th of December and 2 nights in January. I'm trying to look at the junction U band in the ultraviolet to see if we can detect a series of intense flare activity. Because one of the problems with the test mission is that the band is way in infrared. So you may be missing a lot of high energy flares that are more blue or more intensive. I'm not sure. I've also started to get involved in radio astronomy. I've used the IAA in New Mexico. I've used the giant meter telescope in India. This is an image taken many, many years ago of the Arecibo. I'm actually standing up where the instruments are, overlooking the array. Now, you probably don't see it, but I have a hand holding onto a rail, a white knuckle job. I hate heights. I often do. So it took a lot of my energy to get out there in the first place. Unfortunately, some of you may know that Arecibo no longer is functional. The instrument frame collapsed on top of the array, and it's no longer working. You may ask, why do you want to look at in a radio frequency? If you look at the bottom diagram, on the left-hand side you have ultraviolet and X-rays. Now you have to need spacecraft in order to see those. If you look at the radio, you can observe from the Earth, no problem whatsoever. So that's one of the reasons why we're looking on the Earth. Many years ago, I was at a meeting, and Terry goes to these meetings as well. There's astronomical science group environment, is that what it's called?
Sorry, what?
The astronomical science group environment. Yeah. So many years ago, there was a meeting down in Galway. And I drove down early in the morning and I stayed over and I went for dinner with a friend of mine. And after a nice dinner and a couple of glasses of lemonade, we got talking about a paper that had just appeared a few months earlier in Nature. And this guy had these crowd of mostly PhD students reported radio emission from a brown dwarf. Now, I remember Aaron Golden asked me what I thought of it, and I said, no, it's a totally wrong interpretation. It's not a solar flare that they're observing. It's something like Jupiter. It's an auroral activity. So following that discussion, we applied for radio time in two different telescopes. This is data taken in Arecibo, and one of the objects that we picked was a 1.9 day rotator, a brown dwarf. And you see these pulses. The middle panel, you see these pulses every 1.95 hours. When you look even at the individual pulses, there's a lot of substructure in these things. And what we're basically seeing is, if you imagine that you're looking at a lighthouse and the light goes around, that's what you're seeing every couple of hours. This basically turned out to be entirely. This is an image. This is probably what we're actually seeing in these stars. This is a movie taken off the roll on Earth from the International Space Station. And what we're seeing in these stars is that it's probably slightly tilted a bit, and it just rotates around every now and again. This is a movie of this star. You can see the movie playing down the right hand side. The mission switches on and off, comes on every It's on every 1.95 hours. Based on our observations over the years, we found that these objects pulse. show aspects very similar to planets, and they're very strong magnetic fields. Now, having failed in my attempt to get a Nobel Prize, there are lots of astronomers who like to come up with all these terms, like black holes. Right? You know where black holes came from? The guy, Wheeler from Princeton, came up with this term, black hole. Same with brown dwarfs. So everybody likes to come up with a thing that's named after them. So we can't get a Nobel Prize, get an object named after you. So we thought to ourselves, let's see what top line headline we could think of. So these objects pulse. So you've got P, they're ultra cool, you've got U, and they're dwarfs, you've got D. So what else do you need? Well, not all these objects show radio emission, so they're sporadic. S-P-U-D. So what we had hoped was that headline journals, Irish astronomer discovers sponge in space. But unfortunately, we met a very dour referee who had no sense of humour. And he insisted that we take this sponge out of our paper. The only time I can mention it is here now. Unfortunately, the only sponge you're ever going to get is where you dig in the field. So with that, folks, I'm going to say the end.